All right, so I'm going to look at some different properties of vectors. Now, in a lot of cases, vectors can be treated using the laws of algebra that you would already know, but it's not necessarily obvious that that's the case. So what we're going to do is step through a few different properties. First one is what's called the commutative law of vector addition. Okay, that just means that a plus b equals b plus a. And just a visual demonstration here, if I've got some vector a and I add vector b, remember when you add vectors, you go tip to tail. So tip to tail, and then your resultant vector is this one here. So this would be vector a plus b. Similarly, if we did it the other way around, we did vector b plus vector a, we would get this vector here. But you'll notice that the size and direction of these purple vectors is exactly the same. So we can say that vector addition is commutative. It doesn't matter in which order you do things. So that's the first one. All right, the next one is what's called the associative law of vectors. So vector a plus vector b added together plus vector c is the same as vector a plus vector b plus vector c, okay, which is basically the associative law of algebra, but now with vectors. Just to show you what's going on, vector a plus vector b would give us, this is a and b, and then here's vector a plus b if we added them first. And then we add on some other vector c. So now I've got a plus b plus c. So now we're going to get a vector that's going to go from the base of the purple one to the top of C. So we're going to get this. So this would represent vector A plus vector B added together, and then you're adding vector C to that. But you will agree, hopefully with this next part, that if we do vector A plus vector B plus C, so if we now add B and C together first, we're going to get this vector, B plus C, and then we add A to that, and then we get this situation here. We get vector A plus B plus C, but you'll notice again that this black line has the same size and direction as this black line here. Remember, it doesn't matter where in space they are, as long as the vector has the same size and magnitude, then they're equivalent. So this vector is the same as this one. So that shows us that the associative law of vectors holds true. Next one, the zero vector. There's not much we can say here. Hopefully pretty explanatory. If you've got some vector A and you add the zero vector to it, so a zero vector has zero size to it and no direction. If it's got no size, you can't be pointing in any direction. So vector A plus the zero vector is just vector A. There's not really any other way to show it. You're just adding nothing. It doesn't change anything. Okay, the next one's what's called the additive inverse. So if we've got some vector A, it looks like this. Okay, so that takes us to some other point. All right, and then we add vector negative A. Well, that's going to come back in the same direction because if it's negative vector A, then it's just pointing with the same size in the opposite direction. So we're coming back on ourselves. And so basically we get nothing, right? We end up back where we started. We end up with the zero vector. We have nothing. So that's called the additive inverse. In number land, 2 plus negative 2 is 0. In vector land, vector A plus negative vector A is the zero vector. Okay, next one. This one's a bit more interesting. It's called the distributive law. So if we say L multiplied by vector A plus B, that's the same as L multiplied by A plus L multiplied by B, just like the distributive law in algebra. Here's just a little demonstration. Vector A plus vector B gives us this purple vector here, vector A plus B. This slider at the top here changes the value of L. So you can see if I scale that up, if I scale A and scale B up, A plus B gets scaled up in the same way. So that sort of shows this left-hand side. And yeah, I think you would agree that this holds true. It's kind of hard to describe without sounding like I'm just repeating myself. But yeah, hopefully you can see that that is the case. Okay, the next one's a bit more interesting. It's what's called the compatibility of multiplication of vectors. So if you've got two scalars, P and Q, which are just elements of real numbers, you've got some sliders here for P and Q. If you take PQ multiplied by vector A, that's the same as P multiplied by Q multiplied by vector A. Okay, so let's just pick some values for P and Q. Let's pick Q to be 2.5. Okay, so in red here, we've got P multiplied by Q times vector A. But you can see that's the same as the blue one. Nothing too surprising here, I would hope. Basically, you can multiply P and Q as the same as multiplying P multiplied by Q times vector A. So that's just one of the properties we need to be aware of. And the last one's very straightforward again. Can't really show much here, but 1 multiplied by vector A is just vector A. So hopefully that made some sense. Good luck, and I'll talk to you soon.